Hello students, in this video we'll discuss several consequences of the Cauchy-Riemann equations. Let's recall that if f is a complex differentiable function, recall if f maps omega into c, omega open is holomorphic. Then f equals u plus iv satisfies the Cauchy-Riemann equations. Cauchy-Riemann equations state that partial part bar c bar is equal to 0, which is equivalent to what? Stress lever is set to equivalent to x equals uy and y exactly. Okay, those are the equations. Oh, so that u and here are more different. I have as many derivatives over. I shall regularity sums assume that u and v are infinitely differentiable. We have to prove that actually. For now, let's just assume it. Okay. Then uxx would be equal to vxy. And vxy and the negative vxy, do a y derivative here, is uyy. So if I add these equations together, what can we conclude? Adding these equations together, I have that uxx plus uyy is equal to 0. And that says that u is a harmonic function, right? This is exactly equivalent, saying that Laplacian of u is equal to 0. Right? I can do the same trick with the y's, right? Take a y to this equation and say that uxy is equal to what? Uxy is uyy, vyy. And then I can do a x derivative of this equation over here. Then uxy is equal to negative vxx, like so. Adding these equations together imply that vxx plus vyy is equal to 0, or Laplacian v is equal to 0. So what we conclude these expressions over here? The Cauchy-Riemann automatically imply what? Cauchy-Riemann automatically imply u and v are harmonic, right? So proposition, let's just summarize that proposition. F equals u plus iv holomorphic implies u be harmonic. Beautiful, right? Gives us our bridge between real analysis and blood analysis. Excellent. All right, here's our proposition. Suppose that either the real part of a differentiable function, real part of f, is a constant, or imaginary part of f is a constant, where f is holomorphic. So either the real and imaginary part of the holomorphic function are constants, then the holomorphic function itself has to be constant. That's not constant. So how you prove something like this? So what does this first equation? So the proof is straightforward, right? So proof: if u is a constant, then this implies that ux is equal to 0 and uy is equal to 0. The derivative of a constant is 0. Ux equals 0 implies that vy is equal to 0 by Cauchy-Riemann, and uy equals 0 implies what? Implies that vx is equal to 0. And these two things imply that v is a constant. So now, u is a constant and v is a constant. If both u and v are constants, then your function must also be what? Constant plus I constant into complex like constant. Well, the other direction, easy, right? The other direction says what? If v is constant, then we're going to play the same game. This implies that vx equals 0 and vy equals 0. Vx equals 0. Like Riemann implies that uy is equal to 0. And then Vy equals 0 implies by Cauchy-Riemann that Ux is equal to 0. And that applies to each of us. So this implies that U is a constant. And again, now I have that U is a constant and D is a constant, so it proves that the function is a constant. Now, one other thing over here we should mention, which is another sort of proposition. Oh, it's a little bit harder over here. Proposition is what? Is that if modulus of f squared is constant, then that implies that f is constant. The easiest way to see this is using the open mapping theorem, which we haven't proven yet, but we could see later on the built-in mapping theorem is sort of like this, right? The whole point is that you have u squared plus v squared is a constant c. That implies that ux plus vx is equal to 0. It implies that uy plus vy is equal to 0 by differentiating that equation implicitly. And now we can get what? And now we can conclude that this says that u times what? What's ux? Ux is negative vx plus vx. And then over what? And then u and then uy is going to be what? Whoops, that's the ux. So ux is what was vy. So that's going to be vy. Vy. Vy equals 0. And it's going to be a negative vx plus what? Plus vy equal 0. Okay? And now let me multiply the top equation by what? I multiply the top equation by, I want to get these things at the same coefficient. I'll multiply these equations by v, so that's going to be a v, that's going to be a v squared. Multiply this by u over here, so that's going to be a u, and that's going to be a u squared. So if I add those equations together, the vx terms are going to cancel out. You're going to be able to conclude that u squared plus v squared times what? U squared times v squared, or vy, is equal to what? So adding these equations together, you have u plus v squared, the vx will cancel out, is equal to 0, and that's going to force vy to be 0. Y is equal to 0, right? Because that's not 0. And by the same arguments, if vy is equal to 0, you can prove easily that vx has to be 0, right? So then vx has to be 0, and then v is going to be a constant. So v is a constant. Once you have that v is a constant, now I can run this scheme over here. We can conclude that u is a constant, right? So in other words, when modulus of f is constant, you can implicitly differentiate it, solve for the vy, vx. You conclude that the function f itself has to be constant. So we're seeing that there's a really, so if I impose some sort of very stringent conditions on the real part and the imaginary part. In other words, I'm imposing a topological condition saying that the real part is constant, right? In other words, you're being mapped onto a single line in the complex plane, right? Or you're maybe mapped to a single line over here, or you mapped out to the unit circle. So those are dimensional reductions. This is a mapping onto a line, this is mapping onto a line, this is a mapping onto a circle. In any of those dimensional reductions, the analyticity forces the function to be a constant itself. So there's actually a regularization mechanism which prohibits you from doing a dimensional reduction with these analytic functions, which is a very powerful tool, which we're going to see in further videos when we discuss the open mapping theorem. Thank you very much.